What if the most powerful force affecting Earth right now isn't coming from beneath our feet, but from 93 million miles away? Over the past few days, scientists have detected intense and unusual solar activity, massive solar flares, powerful energy bursts, and disturbances that are pushing Earth's magnetic field to its limits. And almost immediately after these events, strong earthquakes began striking different parts of the world, some with little to no warning. So the question is no longer if something is happening, but how far this escalation could go. Could the sun actually influence seismic activity on Earth? Are these earthquakes random events? Or are they early signs of a chain reaction we don't fully understand yet? In this video, we'll break down the real scientific data, the patterns researchers are quietly tracking, and why some experts are becoming increasingly concerned about what may happen next. This isn't speculation. These are measured signals, recorded anomalies, and timelines that are raising serious questions. Stay with me until the end, because once you see how these events line up, and what could happen if solar activity continues to intensify, you may never look at the sun the same way again. This could be the beginning of something much bigger. It started, not with a rumble in the ground, but a flicker in the sky. On the morning of January 4th, 2026, the sun began changing. It was quiet the week before, not silent, but ordinary. A few active regions rotating across the limb, the usual minor flares, the predictable hiss of solar wind brushing past Earth's magnetosphere. Then came AR 3762, a new sunspot, vast and tangled, rotated into view along the sun's eastern limb. It wasn't just big, it was magnetically complex. Astronomers from observatories in California, Italy, and New Delhi noticed immediately. The magnetic structure was a delta-class configuration, meaning that opposite polarity fields were packed closely together, tightly wound like a coiled spring. That's a warning sign. Because when those opposite fields snap, when the magnetic lines reconnect, the sun doesn't whisper. It explodes. By mid-morning, the data was conclusive. AR 3762 had formed a polarity inversion line spanning over 60,000 kilometers, enough to store energy for an X-class flare, the most dangerous kind. Alerts were quietly issued. Space weather centers updated probabilities for eruption. Satellite operators were advised to monitor telemetry, but publicly it was calm. The sun had shown this behavior before, and most of the time it passed without incident, until it didn't. On January 5th at 3:20 UTC, the magnetic fields collapsed. But instead of a flare alone, the sun released a powerful coronal mass ejection, a CME, a vast cloud of charged plasma accelerated into space at over 1 million miles per hour. The direction, aligned almost perfectly with Earth's orbital plane. Unlike solar flares, which emit light and radiation, CMEs are different. They are mass, structured, turbulent plasma embedded with magnetic fields, and when they collide with a planet like ours, they don't just light up the sky, they compress magnetic fields, they induce currents, they shake the invisible shields we depend on to protect life from radiation. This one was big. NASA's Solar Dynamics Observatory clocked the CME's initial velocity at 1,900 km per second, enough to reach Earth in just over 36 hours. But it wasn't just the speed that caught attention, it was the magnetic orientation. Embedded within the CME was a strong southward-pointing magnetic field. That's critical. Earth's magnetic field points north. When a southward field meets a northward one, it creates what scientists call magnetic reconnection, a kind of forced handshake that allows solar particles to penetrate more deeply into Earth's system. It's like opening a door. By January 6th at dawn, that door was fully open. The first impacts were subtle, a shift in satellite drag, a spike in auroral brightness, GPS signals scattering over high latitudes. But beneath those symptoms, Earth's magnetic field was folding, compressing, reacting. Deep beneath the surface, currents began to stir, and then the ground moved. Seismometers in Chile, then Japan, then Indonesia, one by one, began recording activity. Not aftershocks, not foreshocks, earthquakes, fast, shallow, sudden. In the span of hours, the world had changed. What triggered the shaking wasn't a build-up of pressure beneath the crust. It was a push from above, a celestial impulse, delivered by the sun and felt by the Earth. And this time, it didn't just affect one fault, one region, or one plate. It echoed. By the time the first tremors reached seismographs along the Pacific Ring of Fire, Earth's invisible armour was already under siege. Most of us go through life unaware of it. The magnetosphere, a protective shell of magnetic energy wrapped around our planet. It deflects solar radiation, repels charged particles, and shields our atmosphere from being stripped into space. Without it, Earth would resemble Mars, barren, dry, exposed. But on January 6, 2026, that shield was pushed to its limits. The coronal mass ejection that erupted from the Sun 2 days prior arrived in full force just after 04 UTC. Travelling at nearly 2 million kilometers per hour, the wave of plasma slammed into Earth's magnetic field like a tide hitting a seawall. The magnetopause, the boundary between Earth's field and interplanetary space, compressed inward. Normally sitting about 60,000 kilometers from Earth on the day side, it buckled, retreating inward to just under 47,000 kilometers. For satellites in geosynchronous orbit, that was dangerously close. The compression wasn't uniform. On the night side of the planet, Earth's magnetotail, the long-stretched portion of the field blown back by the solar wind, began to warp. Space weather instruments aboard NASA's Themis probes detected sudden increases in tail density, pressure pulses moving like shock waves through the extended magnetic structure. These weren't passive fluctuations. They had direction, shape, and rhythm. And then, in a coordinated burst, the entire tail snapped back, a phenomenon called magnetic reconnection. It's a process that releases enormous energy, not unlike a coiled rubber band suddenly let go. And when it happens in space, that energy doesn't stay there. It travels. At the poles, auroras erupted in unexpected latitudes. Skies above Montana and southern Germany lit up in pink, green, and purple. Ground-based magnetometers began to vibrate. In places like Tromsø, Kiruna, and northern Quebec, sensors used a gradual magnetic drift began recording sharp, erratic spikes, changes in the Earth's field occurring over seconds, not hours. But it was what happened deep within Earth's crust that caught scientists off guard. In several monitoring stations across the Pacific, electrical engineers overseeing long-distance power transmission lines noticed something strange. Ground currents were rising. These aren't the kind of currents we use in homes. These are geomagnetically induced currents, slow-moving surges that flow through the planet itself, normally harmless. But during solar storms they can reach thresholds high enough to fry transformers, and that's exactly what began to unfold. In the early hours of the storm, a substation in northern Japan went offline. In Alaska, protective relays triggered shutdowns preemptively. In Norway, engineers noted transformer temperatures rising despite no change in load. It was a silent creeping pressure, the kind that doesn't make headlines, but rattles infrastructure from beneath. But deeper still, below the cities, the soil and the fault lines, something else was changing. In California, Japan, and parts of Indonesia, scientists monitoring deep borehole electrodes noticed a sudden change in subsurface electric fields. These sensors, designed to pick up shifts in the planet's natural voltage, recorded directional changes that mirrored the magnetotail's recoil. For years, geophysicists have theorized that shifts in the magnetic field might influence the crust, but this was data, real, time-stamped, spatially aligned. The crust wasn't just a passive slab of rock. It was reacting. Somewhere between the clouds of plasma in space and the tectonic plates below, an invisible dialogue was unfolding. Energy was moving not just across space but into the Earth itself. And when the field bent too far, Earth began to bend with it. At first it looked like noise, background rumbles, the kind that populate seismograph logs every day. Minor tremors, nothing unusual. But within minutes, the pattern began to emerge. This wasn't noise, it was a signal. And it was global. The first event struck off the coast of central Chile, a magnitude 6.4 earthquake just before sunrise local time. It jolted residents from sleep in Santiago, cracked windows in coastal towns, and sent emergency response teams scrambling. But what puzzled seismologists wasn't the quake itself, it was the fault line. The rupture occurred on a segment that had recently discharged energy during a 2023 earthquake. That segment wasn't due for movement. GPS strain models showed a neutral stress profile, and yet the Earth had moved, forcefully and without warning. Just 33 minutes later, another tremor struck thousands of kilometers away, this time near Japan's Izu Islands. It registered 6.1 on the moment magnitude scale. There were no injuries, but the quake triggered alarms across the Japanese Meteorological Agency. 2 major quakes on opposite sides of the Pacific within an hour. That would already be unusual. Then came Indonesia. A magnitude 5.8 quake shook Sulawesi's southern coast. Villagers reported shaking that lasted nearly 20 seconds. Walls cracked, chickens scattered, and still, no foreshocks, no prior tremor activity, nothing. It didn't stop there. In California's Imperial Valley, a known zone of geothermal instability, a different pattern emerged. Not a single large quake, but a rapid sequence of microquakes. In just 90 minutes, over 50 separate seismic events were logged. Each was shallow, most under 5 kilometers deep. None caused damage, but the swarm was intense and sudden, and more importantly, it was timed perfectly with the moment Earth's magnetosphere compressed to its minimum threshold under the CME's impact. This wasn't a series of local tectonic failures, this was something bigger. Seismologists began mapping the events globally. Within 6 hours, earthquakes had occurred in Chile, Japan, Indonesia, California, Greece, Turkey. Each event individually might have fallen within statistical noise, but together, they painted a disturbing picture. Most earthquakes happen independently. Local tectonics, stress accumulation, lithospheric weakness, regional fault dynamics explain the vast majority of them. But what January 6th revealed was a kind of synchrony. Quakes were appearing in regions that had no mechanical relationship to one another. The Pacific Plate doesn't speak to the Anatolian fault line in Turkey. California's swarms don't trigger motion in Greece. And yet, the Earth moved, not along a line, but across a sphere. The tremors were rapid, shallow, and oddly impulsive. In Chile and Japan, moment tensors, mathematical descriptions of seismic force, showed more vertical uplift than expected. That means the crust didn't just slide, it was pushed, as if some upward force had joined the usual horizontal mechanics of fault motion. That push, scientists now believe, may have come from above, or more precisely from within. Because under the influence of solar magnetic pressure, Earth's internal electric currents, normally dormant, may have activated. In regions with conductive crust, these currents can build, and when they peak, they can influence pore pressure, fracture integrity, even fault slippage. What January 6th showed was a planet primed to respond. Not randomly, but quickly. In the language of Earth science, this wasn't a cascade. It was a resonance. One solar storm, one planetary system, and one chain of motion that made the ground long before the ground cracked in Chile or the ocean floor shifted near Japan. Earth's upper atmosphere was already pulsing with invisible turbulence. High above the surface, at altitudes between 60 and 1,000 kilometers, floats a region few people think about, the ionosphere. It's where the atmosphere begins to blur into space, where atoms, energized by solar radiation, lose electrons and become ions. It's the zone that makes long-distance radio communication possible, the layer that glows with auroras during storms. But it's also something more. It's a mirror, one that reflects the sun's behavior in real time. On January 5th, as the CME barreled toward Earth, ground-based radio stations began to notice strange propagation effects. VLF, very low frequency, radio waves began bending in erratic paths. Some skipped further than usual, others vanished altogether. And satellites in low Earth orbit recorded unexpected fluctuations in the total electron content, a measurement of how charged the ionosphere was becoming. But none of this was abnormal on its own. Solar storms often shake up the ionosphere. What caught researchers' attention was the pattern. Over South America, over Japan, over the Western Pacific, at precisely the locations where quakes would occur the next day, the ionosphere began to ripple, not laterally, but vertically. These were not the broad, sweeping shifts typically associated with solar flares. These were localized columnar distortions, narrow spikes and dips in electron density, as if invisible towers of ionization were punching downward from space into the atmosphere. And beneath those towers sat Earth's fault zones. The phenomenon has a name: pre-seismic ionospheric anomalies. In some past earthquakes, most notably in Japan's Tohoku quake in 2011, ionospheric irregularities were detected minutes to hours before the main shock. The science is still young, the mechanisms aren't fully understood, but there's a growing suspicion that electrical coupling between the crust and atmosphere, especially under the influence of a solar storm, might reveal stress before rupture. On January 6th, those anomalies weren't subtle. Over Japan, the GeoNet satellite array recorded a rapid increase in localized electron content, just 45 minutes before the Izu Islands earthquake struck. Over Chile, tech measurements spiked and then collapsed in a narrow corridor along the subduction zone where the quake occurred. In both regions, the disturbances were short-lived, lasting between 20 and 60 minutes. Then they vanished. But their alignment with the epicenters was uncanny. To many researchers, this was not coincidence. It was communication between layers of Earth's system we rarely consider connected. The sun had sent a charge, the ionosphere had lit up, and deep in the crust something stirred in response. Some theories suggest the solar storm overloaded the ionosphere with energy, creating downward electrical currents, quasi-static electric fields that reach toward the ground like invisible tendrils. When these tendrils touch regions with high crustal conductivity, such as volcanic belts, oceanic trenches, or tectonic plate boundaries, the energy doesn't just dissipate, it resonates, and that resonance may be enough to tip a stressed fault into motion. Not as a primary cause, but as a trigger. The idea is still controversial, but what's not in question is this. The ionosphere saw the earthquake before the earthquake happened. On January 6th, it pulsed with precision, marking zones that were about to break. And if we can learn to read those pulses in real time, we may one day predict what still seems unpredictable, not by watching the ground, but by listening to the sky. In earthquake science, some events arrive as expected. A slow build of tension, a period of foreshocks, then a final rupture. But others come as a surprise. A rupture where no stress should have been. A tremor with no warning signs. A break in the script. On January 6th, Chile experienced exactly that. The 6.4 magnitude quake that struck near the coastal Atacama region wasn't just powerful. It was, by all known models, premature. The fault segment that gave way had already ruptured just 2 years earlier during a moderate quake that released most of its accumulated stress. Geophysicists monitoring the region considered it stable, at least for the foreseeable future. Satellite-based strain data from GPS towers showed neutral displacement. The fault was calm, quiet, dormant. But at 0548 UTC, that calm shattered. The quake began shallow, just 8 kilometers below the surface, and it struck fast. Not with the long, groaning build-up of a slowly unzipping fault, but with a jolt. A sudden, forceful impulse that felt more like a detonation than a tear. It rattled buildings in La Serena. Power flickered in Copiapó. But seismologists were focused on something far more perplexing than the shaking itself, the waveform. Every earthquake has a signature, a pattern of energy that travels through the Earth in distinct waves. P waves come first, fast and sharp. S waves follow, slower but more destructive. And the full waveform gives insight into how and where the rupture began. But this quake didn't follow that pattern. When seismograms from the region were analysed, something stood out. The first arriving waves didn't match the typical compressional P waves. Instead, they showed vertical ground displacement, rapid uplift, not shear or slip. That means the ground didn't just slide past itself, it rose, as if pushed from below. Even stranger, there were no precursors, no microquakes, no foreshocks. The quake emerged from a region that had been seismically silent for months. In fact, data from local stations showed lower than average background noise in the days prior, as if something had muted the crust. To understand how unusual this is, you need to consider the mechanics of a tectonic fault. Normally, stress accumulates slowly as tectonic plates grind against one another. Friction locks the plates in place until the stress exceeds the frictional resistance, triggering a slip, the earthquake. But that model assumes one thing: internal force buildup. The January 6th Chile quake, however, appears to have been triggered externally. Moments before the quake, Chile's geomagnetic sensors, part of a national network installed to track space weather impacts, detected a brief but sharp disturbance, a surge in horizontal magnetic field intensity. The cause? The CME from the Sun had just compressed the local magnetic field. At the same time, telluric current monitors, instruments that measure electrical flow through the ground, spiked. These currents are typically low-level, part of Earth's quiet electric environment. But during the storm they surged dramatically, flowing along conductive faults and mineral seams like wires in a circuit, and where those currents concentrated, pressure changed. One theory gaining support is that the electrical energy induced by the storm may have caused poor fluid pressure inside the fault to rise, subtly, but enough to weaken the friction holding the fault together. When the final threshold was crossed, the fault slipped, not because it was ready, but because it was nudged. That's what made this quake so alarming. It wasn't on schedule. It was triggered. And if that's true, if a solar storm could release a quake from a fault scientists thought was quiet, then the boundary between Earth science and space weather just got thinner. What we once considered solid ground may be more reactive than we realized. Imagine Earth not as a passive sphere of rock and water, but as a dynamic, reactive system, an electrical body, quietly charged and periodically jolted. Now imagine that the crust itself behaves like a capacitor, storing and discharging energy not just from tectonic movement, but from the sky above. On January 6th, that theory felt less like speculation, and more like a diagnosis. The idea of Earth's crust acting as an electrical capacitor isn't new. It's been whispered in the halls of geophysics for decades, often dismissed, rarely embraced. But the data gathered during this solar storm has revived interest in what many once considered fringe science. Here's how it works. A capacitor is a simple system. Two conductive surfaces separated by an insulator. When voltage is applied, one side accumulates positive charge, the other negative. Energy builds, and when the stored charge exceeds a threshold, it releases. Sometimes gradually, sometimes violently. Now scale that concept to a planetary level. Earth's crust is riddled with minerals that conduct electricity, iron oxides, graphite-rich veins, saline groundwater channels. Underneath lies the mantle, less conductive but not inert. And above sits the ionosphere, a charged atmospheric shell influenced directly by solar radiation and geomagnetic activity. Between these two, the crust and the sky, Earth's surface becomes the dielectric, the insulator. When the Sun sends charged particles, especially during an event like the January 6th CME, Earth's magnetic field funnels them toward the poles and into regions with lower geomagnetic resistance. There, these particles interact with the ionosphere and drive electric currents downward into the ground. These are called telluric currents. They flow silently, invisibly, through the Earth. But when they encounter certain geological structures, especially fault zones rich in conductive rock, they don't just flow, they accumulate. That's where the capacitor model comes into play. In areas with high crustal conductivity, these currents can build electrical pressure. This doesn't mean the ground becomes electrically hot in the way a power line does, but it does mean voltages across faults can change, and that shift in voltage can influence the stability of locked faults by altering something far more critical: pore pressure. Fault zones aren't dry, they're laced with fluids, brines, groundwater, even hydrothermal systems, and under normal conditions these fluids sit in equilibrium, held in place by overlying rock pressure and capillary forces. But introduce an external electric field, and something subtle happens: electrokinetic coupling. That's a fancy term for how electrical fields can cause fluid to migrate through porous media. In simple terms, the electricity moves the water, and when fluid migrates into a fault zone, it can reduce friction, just a little. But in a fault system already near its critical threshold, a small decrease in friction is enough to tip the balance. On January 6th, this is exactly what some scientists believe happened. Satellite data from NASA's SWARM mission showed elevated geomagnetic activity over fault-rich zones in California, Turkey, and coastal South America, the same regions where seismic activity soon followed. Ground-based magnetotelluric arrays recorded synchronous pulses of electrical energy moving through the crust in Chile and Japan. And in California's Salton Sea, a known geothermal area, Localized electric fields spiked just minutes before a microquake swarm began. Was it coincidence? Perhaps. But the alignment, solar impact, crustal charge, seismic release, happened too quickly, too cleanly. It was as if the Earth's crust had waited for a cue, and then discharged. If the capacitor model is correct, then January 6th was a case study in planetary-scale energy transfer. A demonstration that Earth doesn't just receive energy from within, it reacts to energy from without, and the boundary between geophysics and heliophysics just became electrified. In California's Imperial Valley, the ground didn't just shake, it moved, quietly, vertically, in a pattern that seismologists are still struggling to explain. On the morning of January 6th, just as Earth's magnetosphere endured its peak compression, under the weight of the incoming solar storm, sensors buried deep in the desert soil began transmitting an unusual signal. It wasn't seismic noise, it was something subtler, uplift, vertical ground motion, rising and falling by centimeters, measured not in rumble, but in pulse. It happened near the Salton Sea, a region known for its geothermal activity and complex fault systems. This desert basin, where the Pacific and North American tectonic plates interact in strange fluid ways, is a hotspot for microquakes, geothermal energy extraction, and silent subsurface shifts. But even here this motion stood out. GPS towers planted across the Imperial Fault Zone began to register a rapid change in elevation. Not gradual, not creeping, but sudden. Short bursts of upward displacement, followed by brief stabilization, and then another spike. Within 90 minutes, 3 such pulses were recorded. Each corresponded with distinct surges in ground-based electric field intensity, logged by nearby magnetotelluric sensors. What makes this remarkable is the timing. Those pulses occurred during the exact window when Earth's magnetic field was compressed to its minimum, the tightest moment in the solar storm's impact timeline. Across the planet, Earth's magnetic bubble was squeezed inward. But in the Imperial Valley, it was as if that compression reached the ground, and the Earth pushed back. The vertical displacement was small, just under 2 centimeters in some locations, but the rate of change was fast enough to activate the earthquake early warning system, which is normally triggered by lateral fault movement. For nearly 90 seconds, algorithms flagged a potential larger rupture. None came, but the motion had been real and verified. So what caused it? Theories vary. Some scientists point to geothermal dynamics. The Salton Sea area is riddled with hydrothermal reservoirs, and rising magma or shifting hot water can produce ground movement. But satellite-based infrared scans showed no corresponding thermal activity that day. Others blame fluid migration, underground water being displaced by electric pressure from telluric currents induced by the solar storm, and while plausible, such a mechanism has never been directly observed causing displacement at this speed and scale. A newer hypothesis borrows from the field of electromechanical coupling, the idea that electric fields, especially during geomagnetic storms, can interact with mineral grains in the crust. Certain rocks, like quartz-rich sandstones, exhibit piezoelectric properties. That means they generate electrical charge when stressed, and conversely, can deform slightly when exposed to electric fields. Could it be that the intense geomagnetic disturbance caused localized piezoelectric deformation? The math suggests it's possible, but only in narrow zones where mineral composition, fluid saturation, and electrical alignment converge. The Imperial Valley happens to be one of those rare places. If that's the case, then what we saw wasn't seismic movement, but electromagnetic displacement, a literal rise in the land caused by the sun's influence on rock. It's a bold theory, but one that fits the data better than most. Because one thing is now clear, this wasn't tectonic pressure from deep below. There was no build-up, no stress accumulation, no telltale tremors preceding the motion. Instead, the ground lifted in sync with the sky. A soft, silent motion, mirroring the compression of a magnetic field far above. For centuries, earthquakes have been explained as internal, driven by heat, by stress, by time. But on January 6th, California reminded us that the surface of Earth is never truly separate from the storm in space, and sometimes it rises to meet it. As the Earth rotated through the early hours of January 6th, a strange pressure began building beneath the surface. But it wasn't volcanic, it wasn't tectonic in the traditional sense. What scientists noticed was more nuanced, an invisible hand tightening the seams of the planet's crust, almost like a heartbeat syncing with something above. This chapter of the story didn't begin in a laboratory. It began inside a deep-sea pressure sensor off the Pacific Rim. At precisely 3:42 in the morning, a sudden fluctuation in sub-seafloor tension was recorded. Not an explosion, not a quake, but a long, slow undulation of force that seemed to rise from beneath the mantle and curl outward like ripples through an underground lake. The anomaly lasted less than 60 seconds, but it was enough. Within minutes, more sensors across the ring of fire mirrored the shift. It was as if something had pushed upward from below, not with a jolt, but with a pulse, the kind of motion that doesn't break rock immediately, but strains it, and the longer the strain remains unrelieved, the more unstable the system becomes. This wasn't a random pressure build-up. The data showed clear alignment with electromagnetic surges from the solar event recorded hours earlier. But how could a burst of energy from the sun translate to pressure building beneath the crust of the Earth? The answer lies in how our planet manages heat, magnetism, and pressure as a system, not as isolated variables. Earth is not sealed off from the solar system. It breathes with it. It conducts, it resonates, and it responds. When a strong solar storm hits, one of the immediate impacts is increased ionization in the upper atmosphere. This changes how energy is distributed through the Earth's magnetic field, compressing the magnetosphere on the day side and elongating it on the night side. But the effects don't end in the air. That magnetic squeeze continues downward. Electric currents called telluric currents begin moving through the crust, seeking the path of least resistance. Under certain conditions, these currents concentrate in fault zones, mineral deposits, and deep aquifers. They warm rock. They subtly change pressure gradients. They create friction where none existed before. And on January 6th, that invisible lattice of energy began humming. The crust, already fractured in many parts of the world, became a conductor of stress, not from shifting plates, but from charged particles and currents flowing through deep channels beneath our feet. Pressure didn't build from within. It was induced from above, then magnified by Earth's own structure. In some areas, this translated to a soft groan, a deep frequency that humans couldn't hear, but which registered clearly on seismic equipment as harmonic tremor. In others, it showed up as slight gas emissions, methane and radon rising in areas where no tectonic motion had been detected for years. These were not signs of a typical earthquake cycle. These were pressure signals, induced, foreign, and inescapably linked to what the sun had just done. There were people, too, who felt it in their bodies. Sensitive individuals, especially those living near fault lines, reported headaches, nausea, ringing in the ears. They didn't know about the solar storm, they didn't need to. Their nervous systems were responding to shifts in Earth's electromagnetic field the way animals do before a quake. The scientific community began paying closer attention, not just to seismic alerts but to electromagnetic ones, because what happened in the crust on that morning was not an isolated tremor. It was the sound of tension being applied, without yet knowing where it would release. This was the moment Earth began to hold its breath, and as the pressure beneath our feet intensified, it became clear that something was coming next, something not triggered from below, but from the sky above. By the time dawn broke over the eastern hemisphere, something strange had already begun happening in the upper atmosphere. Pilots flying long-haul routes at cruising altitudes reported a phenomenon they hadn't seen in years, bands of shimmering auroral light appearing far beyond the poles. But these weren't the typical green or purple waves one might expect during high solar activity. These lights came with no colour. Instead, they looked like silent fractures, thin, horizontal bands of distortion that stretched across the sky like ripples in glass. Some described them as white veins, others as cracks in the clouds that shouldn't be there. What was remarkable wasn't just their appearance, it was where they were being seen, over the equator, over the Indian Ocean, and even over the Sahara. At first, many dismissed it as a visual illusion, perhaps refraction, perhaps a reflection off high-altitude ice crystals, but the sensors didn't lie. Multiple weather balloons equipped with radiation counters, magnetometers, and atmospheric density probes recorded the same thing, a thinning. Something in the upper atmosphere had split, temporarily, allowing high-energy particles to surge through. Scientists at multiple observatories compared notes. And what they found was unsettling. These cracks in the atmosphere were magnetically aligned, meaning they didn't follow the shape of Earth's weather systems. They followed the path of the sun's energetic wave, like scorched seams left behind by an invisible hand carving a pattern into the planet's magnetic shell. It was in this moment that one critical realization emerged. The atmosphere hadn't broken in the way we break material. Instead, it had become resonant. It had begun vibrating in harmonic layers, like a bell being struck repeatedly by pulses of energy. These resonance lines created zones of instability, temporary corridors where solar radiation could leak through in higher concentrations. The consequences were not hypothetical. In South America, airline crews rerouted flights to lower altitudes to avoid cabin radiation spikes. In Australia, emergency satellite protocols were activated after high-frequency communication bands went dead. And in Eastern Europe, livestock began acting erratically, herds moving together in tight circles, birds flying off course, as if guided by a field humans couldn't perceive. This wasn't just a weather story. It wasn't just an electromagnetic anomaly. It was a warning sign. The sky wasn't protecting Earth in the way it usually did. For a few hours, the natural barrier that filters out cosmic chaos had thinned, and the planet beneath had felt it. People on the ground didn't see this happen, but some felt it. Not with their eyes or ears, but through sensations they couldn't explain. A sudden pressure in the chest, a ringing in the head, static that made the hair on their arms lift. All small signals of a much larger shift. Because when the sky cracks open, even for a moment, it changes the entire equation. Not just for radiation exposure, but for the balance of energy between Earth and the Sun. A balance that had held for thousands of years. But on January 6th, that balance tilted. And as Earth absorbed that imbalance, something deeper began to stir. Not in the sky, but in the core. Something ancient. Something waiting. Deep beneath the surface, far below the crust, beyond the slow swirl of magma, past the tectonic plates and the molten iron sea, Earth's core had always been considered a silent sentinel, immense, unyielding and steady. It spun within us, generating the very magnetic field that shields all life from cosmic radiation. But after the January 6th event, instruments around the globe began picking up something new. At first, it was the neutrino detectors, those quiet observers that sit buried in mountain caverns, watching for particles that pass through Earth like ghosts. They registered an anomaly, an uptick in particle noise that wasn't cosmic in origin. The pattern was coming from below, a signal pulsing upward. Not strong, but unmistakable. A frequency that matched nothing we've ever catalogued before. Then came the seismic stations, hundreds of them spread across continents. Most were used to monitoring earthquakes, but what they recorded wasn't seismic in the usual sense. It wasn't a quake, it wasn't a tremor, it was something subtler, deep rhythmic fluctuations in the ultra-low frequency range. A low-end hum like the resonance of a giant tuning fork echoing from the planet's center. Scientists dubbed it the murmur. This murmur wasn't consistent. It pulsed in cycles, every 90 minutes give or take, and each pulse was stronger than the last. That alone might have passed as a curiosity, if not for what it began affecting. In the Arctic, compasses drifted by 2 degrees east in less than 48 hours. In the South Pacific, whale migration patterns veered into confusion, with pods swimming into shallow bays they normally avoided. In mining towns across Australia and Chile, veteran drillers spoke of new vibrations in the bedrock, soft, unnatural waves that seemed to roll in from below. Some geophysicists speculated that the solar activity, combined with the atmosphere's temporary crack, had allowed a surge of external energy to penetrate deeper than ever before, not just into the oceans, not just into the mantle, but into the very iron heart of the Earth. If true, that would mean the core, long thought to be insulated from solar influence, was no longer untouched, and that carried consequences. Earth's magnetic field is generated by the motion of molten iron within the outer core. Disrupt that motion, even slightly, and the entire magnetic shield could shift, triggering pole wander, compass deviations, and in extreme cases geomagnetic reversals. But this time, the shift wasn't coming gradually over millennia. It was pulsing, accelerating. In Geneva, a closed-door meeting was held between leading geophysicists, planetary defense analysts, and satellite calibration experts. Their biggest concern wasn't the murmur itself, it was what might be responding to it. If Earth's core was now resonating in sync with some new cosmic frequency, one amplified by solar activity, then our planet was no longer acting alone. It had become part of a larger feedback loop. An energy chain that might include the sun, space weather, and possibly something else. The murmur, they concluded, wasn't just a symptom, it was a message. But from whom or what? No one could yet answer. Only one thing was clear. The ground beneath our feet had started to speak, and what it was saying would soon be impossible to ignore. It started with a plume over Kamchatka. At first, satellites mistook it for an isolated eruption, just another burp from the volatile Pacific Ring of Fire. But then another column rose in Guatemala, then in the Congo, then Iceland, then Tonga. Within 24 hours, 6 major volcanoes had released ash into the atmosphere, all of them unconnected, all of them dormant or quiet for years. Volcanologists tried to find a unifying cause, an earthquake chain reaction perhaps. But there had been no significant tectonic shifts linking these regions. The plates weren't colliding, the crust wasn't cracking. What they found instead was heat. Subsurface heat rising faster than any model had predicted. Magma reservoirs that had lain cool were now bubbling. Dormant chambers were stirring. The media dubbed it the awakening. But scientists were more cautious, because what they found underneath the volcanoes wasn't just increased temperature, it was rhythm, a timing, a pulse, as if these pressure points on the planet's skin were being pushed, not from the side like in an earthquake, but from below, from the deep earth. And the timing matched the murmur, the same 90-minute intervals, the same gradual escalation. Volcanoes had always been driven by Earth's internal heat, tectonic friction, or water vapor buildup. But this looked different. It looked orchestrated. Global eruptions separated by thousands of miles happening almost in unison suggested something deeper was coordinating them. In Indonesia, sensors beneath Mount Sinabung recorded harmonic tremors, patterns of vibration that suggested magma was moving upward in steady, measured waves. In Italy, researchers at Vesuvius observed a sudden deformation in the caldera floor, one that matched a geothermal swell recorded hours earlier in Chile. It was as if the planet had entered a shared respiratory cycle. Inhale, pressure rise, exhale, ash release. Governments began quietly raising alert levels. Airports near active volcanoes were instructed to reroute flights. Public statements were vague, citing temporary geological instability. But inside geological agencies, the concern was growing. Because volcanoes are Earth's pressure valves, when they start to blow together, it means the pressure is coming from a place far deeper than the surface. One theory emerged from a fringe group of magnetohydrodynamic researchers that the solar storm hadn't just cracked the magnetosphere, it had reached into Earth's core and altered the flow of its magnetic lattice, its internal ion currents. These currents, in turn, were stirring the mantle, and the mantle was stirring the volcanoes. If that were true, then the eruptions were not random events. They were the result of resonance. The planet had been struck. It had absorbed the energy, and now, like a tuning fork still ringing, it was vibrating across every fault line. A few researchers took it further. They noticed that the ash columns, when mapped globally, formed spiral patterns, echoing the twisted loops seen in magnetic storms. The Earth, they warned, was not just reacting, it was responding, and if the volcanoes were answering, then something had asked a very loud question. It began in a bay off the coast of Peru. A small fishing village, used to catching sardines and anchovies, started pulling up something strange in their morning nets. Bright, glistening fish with long dorsal fins and iridescent scales that shimmered like polished chrome. Creatures not seen in those waters for over 70 years. Deep water species. Ones that typically swam thousands of feet below the surface, now floating near the top, gasping. The elders whispered old superstitions. When the deep fish rise, the earth is sick. But marine biologists dismissed it as a fluke, perhaps an underwater landslide or a temporary shift in current. Until it happened again, this time in the Sea of Japan, then the Gulf of Mexico, then the Mediterranean. From every coast came similar reports. Oarfish, gulper eels, strange jellyfish with bioluminescent streaks, species adapted to total darkness, were surfacing in record numbers, some dead, some alive, all out of place. And it wasn't just fish. Divers off the coast of South Africa reported finding coral species typically found only in the Pacific. Microorganisms from Antarctic shells were detected in tropical waters. A Swedish research vessel pulled a pod of temperature-tracking devices from the Atlantic, all of which showed inexplicable thermal spikes not at the surface, but hundreds of meters down. What was rising wasn't just the temperature, it was the entire lower food chain. Sonar scans revealed another anomaly, a migration wall. Millions of fish, not one species but many, had stopped moving. Normally, fish follow seasonal migrations guided by water temperature and salinity. But these fish were gathering, hovering, drifting in place, as if waiting, or listening. And then came the red tide. It bloomed without warning, vast stretches of ocean turning crimson as algal blooms spread across coastlines in less than 24 hours. In the Philippines, fishermen reported fish swimming straight toward their boats, eyes glassy, bodies twitching. In California, surfers emerged from the water vomiting, their skin tingling with mycotoxins. In Norway, dolphins beached themselves in the dozens, and yet satellite imagery showed no natural cause. The winds were calm, temperatures were not extreme, nutrient levels were stable. The oceans, it seemed, were reacting to something, but no one could agree on what. Then a marine geochemist from Brazil noticed a pattern. The deepest salinity shifts were occurring exactly 90 minutes apart, just like the pulse. The oceans weren't heating evenly, they were being agitated, like a bowl of water placed atop a vibrating table. And what disturbed scientists most wasn't just the rhythm, it was the direction. The disturbances weren't coming from above, they were rising from the ocean floor, as if something from the mantle, something ancient or activated, was pushing upward. Some speculated it was a seismic effect, others suggested methane hydrate releases, but a growing faction began whispering about the unthinkable, a biosignal, not from a machine or technology, but from life itself, something old, something deep, something that had heard the pulse and answered back. Marine myths resurfaced, tales of leviathans, of sleeping colossi beneath the crust, of the ocean remembering things the land forgot. And as the fish continued to rise, gleaming, confused and ancient, the question grew louder. What exactly had they heard? And what was making them come up now, all at once? It began with a hum, not the sound of wind or sand, but something lower, deeper, a resonance that vibrated the soles of your feet if you stood still long enough. In the middle of the Atacama Desert in Chile, a team of climate physicists stationed near an abandoned radio telescope array recorded the phenomenon first. The instruments weren't picking up static. They were picking up motion, from beneath the sand. At first, they assumed it was seismic, a harmless tremor. But the readings were off. No waveforms, no quakes, no epicenter. Just a rhythmic swell, a pulse. Every 90 minutes. It didn't register on earthquake maps. It didn't affect buildings, but it moved the sand. Fine grains lifting slightly, then settling, like a shallow breath, barely visible, but unmistakable if you knew what to look for. And once you saw it, you couldn't unsee it. The desert was moving, not in a destructive way, in a responsive one. Then came the pattern shifts. Satellite imagery confirmed microundulations in dune formations. Normally, these changes take months, even years, of constant wind. But now, dunes were shifting shape in hours. Curves appeared in spiral forms. Some formed concentric rings, others arrow-like channels pointing southeast. The shapes weren't random. One researcher overlaid the formations onto a map of the global magnetic field. The alignment was nearly perfect. The desert was echoing not tectonic rhythms, but magnetic ones. News didn't spread, not yet. But a few local shepherds noticed. They spoke of goats refusing to cross certain flats, of herds that began circling in place before suddenly bolting in one direction, always toward higher ground. The elders called it the old stirring, a term not used since before the colonials came. And then, from the Sahara, came another signal, A cluster of nomadic Tuareg tribesmen sent footage to a French anthropologist. Massive heat ripples rolling across dunes, waves of distortion as if the air itself were folding. No sound, no quake, just the feeling of compression and release, as if the desert were flexing. Every 90 minutes, scientists installed geophones in select desert regions, from the Mojave to the Gobi, and in each case, they detected the same low-frequency resonance. Not natural, not mechanical, something in between. The Earth was not cracking, it was communicating. Some theorized it was magnetostriction, where materials physically distort in response to magnetic fields. But there was no metal here, no machines, just dust, salt, sand, and time. Then came the discovery that changed the hypothesis completely. A deep desert drilling operation in Oman, funded by a private aerospace venture, unearthed a layer of subsurface material that shouldn't exist. Vitrified glass, the kind formed only through intense heat or high-energy shock waves, but it was buried 50 feet down, ancient, undisturbed. Embedded within it, fossils, but not of animals, microfossils, bacterial colonies with magnetotactic properties, organisms that align themselves with magnetic fields. Extinct, supposedly, but now returning. The pulse, some speculated, wasn't just stirring the land, it was waking up the memory of Earth's oldest inhabitants. And for the first time, modern science had to face an unsettling possibility. What if deserts weren't dead zones? What if they were the skin of something dormant, responding to a signal they had waited eons to hear again? And if that was true, what would happen when it fully woke up? On the far side of the moon, where no sunlight ever reaches, a series of seismic sensors planted by China's Chang'e 7 mission recorded something it wasn't designed to detect. It wasn't a quake, it wasn't even a tremor, it was a beat. At first, Mission Control thought it was a sensor glitch, some kind of feedback loop from the internal power system. But when they compared it to backup sensors placed along the rim of the South Pole Aitken Basin, the moon's largest and deepest impact crater, they found the exact same signal. Perfectly timed, in sync, every 88 minutes and 47 seconds. The lunar surface vibrated, just slightly, just once, and then silence. Back on Earth, deep space listening arrays cross-reference the signal's rhythm with pulses detected in Earth's own crust, especially across dormant regions like the Namib and Simpson deserts. The match wasn't identical, but it was harmonically related, a ratio, not unlike the mathematical relationships found in musical octaves. In a desperate move for clarity, analysts from the ESA overlaid the moon pulse and desert pulses into harmonic waveforms. They formed a progression, like chords building into a larger structure. And when mapped spatially, the pattern spiraled outward from Earth, not randomly, but toward a singular direction in space, the current trajectory of 3i Atlas. Now it wasn't just theory. Something in the moon was responding, and it wasn't alone. A month later, an amateur radio astronomer in Arizona captured an ultra-low frequency modulation in the ionosphere, timed precisely to when the moon's pulsed frequency lined up over the Pacific. The modulation was faint, but when amplified, it revealed a wave pattern not seen since 1977, the WOW signal. But this wasn't a repeat. It was a reply, structured, binary, containing a sequence of primes nested inside the Fibonacci pattern, but only partially. The last three numbers were inverted, deliberately scrambled. When run through linguistic models, the signal didn't translate into words, but into coordinates. And those coordinates? A tiny region in the Mare Orientale, a walled lunar plain nobody had seriously studied in decades. But now every major space agency was scrambling for time on their best orbital images, because something under that crater had stirred, a subtle dome in the regolith, like pressure building beneath the surface. NASA deployed a high-resolution LRICI scan under the guise of calibrating new instruments, but what they found was movement, just micrometers, but consistent, a lifting and settling motion at the core of the crater, exactly in rhythm with the global pulses. No natural geological process could explain it. The moon, geologically dead for over 1 billion years, was somehow sinking to Earth, and Earth was sinking to something else. One scientist from JAXA quietly remarked, "It's not lunar resonance, it's mechanical entrainment." As if the moon were being tuned. This sent shockwaves through the astrophysical community. If 3I Atlas, this interstellar object, was initiating harmonics across planets, moons, and even deserts, it wasn't a passive traveller, it was a conductor. And Earth was becoming part of its instrument. But no one could agree on the most crucial question. What music was it trying to play? And what happens when the whole system reaches harmony? It began as a fringe anomaly in the sonar data. Off the coast of Easter Island, a deep-sea hydrophone registered an infrasonic tremor that didn't match any tectonic pattern. At first, the noise was dismissed, likely the groan of a subduction plate or a distant undersea landslide. But when it happened again and again, always timed exactly 44 minutes after each moon pulse, oceanographers started paying attention. The sound wasn't random. It had a rise and fall, almost like a breath, and it wasn't alone. Within 2 weeks, similar infrasonic pulses were detected in the Indian Ocean, the North Pacific Gyre, and a rarely monitored trench near the Scotia Plate, places with no shipping traffic, no geothermal vents, and no tectonic unrest. The pulses were faint, but they shared one impossible trait. Each had a precise echo, a return signal. Something was bouncing it back, but not from a continental shelf or seafloor canyon, from inside the water, specifically from a consistent depth of 5,440 meters across every location. The depth itself made scientists nervous because it's known as the Sound Fixing and Ranging Channel, or SOFAR channel. It's where sound travels farthest through water, often thousands of kilometers without losing strength, and whatever was responding from that layer, it was active. The echoes began forming patterns, pulsed trios, Fibonacci sequences, rising harmonics. But the key moment came when the echoes preempted the original pulse by 2 seconds, as if they weren't echoes at all, as if they were answers. This broke every model. Oceans, as far as we understood, couldn't talk back. They could reverberate, resonate, reflect, but not initiate signal patterns. Marine biologists were called in, naval analysts, even geophysicists from oil companies. But none of them had seen anything like it. Then came the image, a Japanese research sub, on an unrelated deep current study near the Mariana Trench, captured high-resolution sonar imaging of a dense vertical structure rising 300 meters off the sea floor. It looked like a column, but with filamentary arms branching like coral, yet it was metallic. It wasn't there 3 months prior. And when the sonar ping hit it, the structure vibrated, just once, and released a burst of acoustic energy that synced perfectly with the infrasonic ocean pulse detected globally that same hour. This wasn't a natural reef. This was a resonator. Overnight, new terms were whispered behind closed doors, terms like aquatic relay, sonic lattice point, and subsurface activation array. Because by this point, it wasn't just one column. 6 more appeared in key oceanic convergence zones, each aligned with a known weak point in Earth's magnetic field. The implication? These structures weren't built recently. They were dormant, buried. Until 3I Atlas arrived. It was as if the comet, or whatever it truly was, had activated them, re-energized an old global system designed to be silent until something specific flew by. And now, Earth's deepest oceans were part of a larger network, vibrating, resonating, and responding. Not to each other, but to an external presence, a presence growing louder by the hour. One question now chilled the minds of every scientist with access to the data. What happens when the oceans finish the song? It was a forest ranger in northern British Columbia who first noticed the anomaly, not in machines or telescopes, but in the trees themselves. His name was Dawson Tellefson, a 32-year veteran of the Old Growth Monitoring Patrol. On January 3rd, while hiking through an unlogged cedar basin, he noticed something deeply unsettling. All the trees, every single one, were tilted 5 degrees east. But it wasn't wind, it wasn't slope erosion. The trees hadn't fallen or broken. They had rotated, subtly, impossibly at the root, their trunks bending in unison like a field of grass beneath an invisible wave. The soil was undisturbed, the moss remained intact. But the trunks had shifted, and the angle of the change aligned perfectly with the sunrise azimuth of that morning, and later with the sky path of Three-Eye Atlas. It wasn't just the angle, it was the silence. Birdsong had stopped, squirrels vanished, insects fell quiet, and most disturbing of all, the local wolf pack, usually tracked by collar data, had left the forest perimeter entirely and moved 12 miles east into cleared farmland. This had never happened in recorded history. When Dawson returned 2 days later, the trees had straightened, but the bark had changed. Under infrared, a soft phosphorescence glowed near the base, barely visible to the naked eye but consistent across dozens of cedar trunks. Botanists initially dismissed it as fungal bloom or lichen behavior. But the glow wasn't organic. Spectral analysis showed trace elements of rare earth metals, specifically neodymium and samarium, often used in magnetic sensors. That same week, something even stranger happened in the Amazon basin. Satellite L-band radar, used to measure canopy health, returned bizarre readings from a 300 square kilometre patch in western Brazil. Tree leaves began emitting a rhythmic reflectivity pulse, roughly every 11 minutes. Leaves, not branches, not bark. The pulse wasn't random. It was a binary pattern, simple, repetitive, alternating. More data poured in. Redwoods in California began showing consistent electrostatic discharges at dawn. Mangrove roots in Thailand bubbled methane in concentric rings. Acacia trees in Kenya dropped all their leaves on the same night, only to regrow them 5 days later, despite being in their dry dormant season. Something had shifted in the global plant nervous system. Yes, plants have one. The phenomenon is known as action potentials, bioelectrical impulses used by certain species to communicate danger, drought, or growth patterns across root networks. Under normal conditions, these signals are slow, limited, and local. But now, they were synchronized globally. A research team in Belgium, using electrodes planted in different species, recorded synchronized electrical pulses every 26 minutes across 5 continents. The signals shared a waveform profile eerily similar to the infrasonic ocean responses from Chapter 15. Earth's oceans and forests were now echoing each other. A chorus was building. The implications were staggering, not just because trees were communicating, but because they were doing so with timing. A timing that tracked the movements of Three-Eye Atlas as it made its slow approach past Jupiter, bending light and magnetism in its wake. One botanist made a chilling observation. She pulled up the path of the Tunguska blast in 1908, the infamous tree-flattening event in Siberia that left 2,000 square kilometers of forest scorched and collapsed, with no impact crater. Then she overlaid the current pulse map. The alignment was near perfect. It was as if the trees remembered, and this time, instead of being caught unaware, they were responding, realigning, reactivating, waiting. But for what? That's what no one could answer. Because if the trees were listening to something above them, and the oceans below them, then Earth's biosphere wasn't just reacting, it was awakening. While forests bent and whispered in quiet synchronization across the planet, a different kind of signal emerged far to the south, beneath a place most would never look, the Ross Ice Shelf of Antarctica. What triggered the discovery wasn't radar or seismic activity, it was salt. On January 4th, researchers at McMurdo Station began analyzing ice core samples retrieved weeks earlier from beneath a subglacial lake known as Lake Mercer. The cores weren't from the surface. They had been drilled from 2 kilometers deep. Ancient, pressurized layers formed over tens of thousands of years. And buried inside that frozen chronology, scientists found something they couldn't explain. At a depth of 184 kilometers, the salinity curve spiked, violently. A concentrated band of crystallized sodium chloride appeared where no such band should exist, locked in a formation of hexagonal plates rather than random molecular lattice. More baffling was the orientation. Under an electron microscope, the crystals weren't random, they were aligned. Every plate angled precisely 33.4 degrees west of magnetic south. At first, the team assumed this was a contamination artifact, a flaw in the coring process or exposure to drilling lubricant. But triple verification scans across 2 separate core samples confirmed it. The anomaly was real, and it was localized. No other layers before or after showed this crystalline behaviour, just a 2 centimetre band. One of the geochemists, Dr. Renata Miles, ran a spectral analysis out of curiosity. That's when the real shock came. The reflection pattern wasn't geological, it was resonant. Specifically, the salt crystals reflected microwave frequencies within the same narrow band being used to monitor 3I Atlas's reflected emissions, signals bouncing back to Earth off the object's surface. The crystals, somehow, had recorded a signature, like a cassette tape storing a specific frequency. When stimulated at 3.221 GHz, the salt emitted a soft repeating echo. Not a sound, but a microrhythm, a modulation of returning energy as if something had once passed through the Earth from above, embedding its imprint deep inside the ice. Dr. Miles called in a glaciologist from Queen Maud Land, a specialist in anomalous ice shelf behaviour. He had recently published a controversial paper about melt pulses rising from below the Antarctic shelf, sudden thermal shifts unlinked to surface temperature or volcanic activity. When he compared his melt pulse timeline with the salt band data, the correlation was impossible to ignore. The pulse had occurred on December 19th, the same day 3I Atlas passed behind Jupiter. Even more unsettling? A second pulse was predicted to occur on January 5th, just 24 hours from the moment the salt anomaly was discovered. If correct, that meant the ice shelf wasn't a passive archive, it was an active receiver. Word reached the European Southern Observatory, where a special team had already been tracking thermal inconsistencies in Earth's mesosphere, specifically over the polar regions. Their satellites had recorded faint but measurable surges in long-wave radiation rising from Antarctica, as if the continent itself was venting energy in synchronized bursts. These emissions mirrored the salt band frequency. Suddenly, a theory emerged, so radical that it bordered on science fiction. What if the salt formation wasn't a fluke? What if it was a marker, an embedded antenna designed to store and replay a frequency over millennia, using Earth's own crystal lattice as a memory substrate? Not designed by us, not even by natural processes, but by something that understood the electromagnetic properties of salt, pressure, and time. And what if the coming pulse wasn't random? What if the buried layer in Antarctica was one of many, scattered across the globe, quietly waiting for a trigger? As scientists scrambled to cross-reference data from Greenland, the Atacama, and Himalayan salt caverns, a quiet alert rang through McMurdo's systems. Seismic sensors beneath the Ross Shelf detected a harmonic tremor. It wasn't tectonic, it was tonal, and it was rising. As the hours passed on the morning of January 6th, something deeper began to emerge, something that reached beneath the crust into the very skeleton of the Earth itself. While tremors were shaking buildings above, instruments buried deep below were detecting something stranger. Not just movement, but vibration. And not just vibration, but resonance, like a tuning fork hit with precision. Except the force wasn't internal. It was coming from the sky. This resonance seemed to align perfectly with magnetic surges registered just after the solar storm. But now, the attention shifted from what had been unleashed above to what was being awakened below. Geophysicists began focusing on areas rich in iron and nickel, places where conductive minerals formed ancient pathways through the planet's interior. These were not random zones. They were fault lines, subduction zones, and tectonic intersections, places where the Earth was already most vulnerable, and now they were vibrating. Imagine this. A solar particle wave hits the magnetosphere. The charge diffuses through the upper layers of the atmosphere, eventually grounding into the crust, but instead of stopping there, it follows pre-existing channels, like lightning through copper wire, diving deeper and deeper. That's what seemed to be happening. Deep Earth conductors, especially in places like Central Asia and South America, began registering low-frequency electromagnetic pulses, not unlike the ones we use in geophysical prospecting. Only this time, no one had sent the signal. It had come from above. These waves didn't just agitate the surface. They seemed to change the pressure balance between tectonic plates, nudging locked faults that had been quiet for decades. That might explain why places with no prior seismic alerts suddenly experienced quakes, while known danger zones stayed oddly silent. The energy didn't follow the patterns we understood, it followed the metal. The result? A kind of underground awakening. Not one loud event, but many small whispers all over the globe. Some reached the threshold of quakes, others only slightly cracked bedrock or shifted sublayers, but it was enough to register on seismic arrays. And when overlaid on the solar activity map from earlier that morning, the pattern aligned with terrifying precision. One area in particular stood out. A cluster of quakes near the Altiplano in South America seemed to pulse in sync with the solar flare's rhythm, not just in energy, but in time. These tremors weren't just echoes of surface activity, they were being driven by a consistent rhythmic force, the same way a microwave vibrates water molecules, only here it was the Earth's mantle being stirred. Scientists began calling this the conductor effect, a theory proposing that solar-induced electromagnetic fields can activate ancient mineral pathways beneath the surface, much like circuits in a primitive computer. If true, it meant the Earth's reaction to solar storms wasn't just surface weather, it was whole planet weather, from the ionosphere to the inner crust. The implications were massive, because it meant earthquake forecasting could no longer be done in isolation. We'd have to track the sun as closely as we tracked faults. And more than that, it suggested something far more sobering. If deep Earth could be tuned like an instrument, what happens when the sun plays a louder note? The question hung heavy in seismic labs across the globe, and for the first time, geologists and solar physicists were meeting in the same rooms, sharing data, aligning timelines, and realizing they had been looking at the same beast from two ends. Because the tremors weren't random, and the Earth, for all its weight and mass, had just responded like a conductor waiting for current, and the current had come. By midday on January 6th, something began unfolding that took the entire global network of geologists, disaster agencies, and solar scientists by surprise. Up until that point, the seismic activity triggered by the solar storm had been scattered. One tremor here, a sudden quake there. It was unnerving, but still within the range of what some called coincidence. But then, almost like clockwork, the tremors began to align, geographically, temporally, and energetically. Seismographs across multiple continents recorded a near-simultaneous uptick in activity. Tiny pulses, deep shocks, and in some cases full ruptures, happening not in a single location, but in linked patterns. First in parts of the Pacific Northwest, then, within minutes, in the Kamchatka Peninsula, then Japan, Chile, the East African Rift, Turkey, Indonesia. It was like watching dominoes fall, not from impact, but from a shared vibration. And this is when a term emerged that hadn't been used since the 2004 Indian Ocean earthquake: cascade zones. A cascade zone isn't just a seismic region, it's a fault system so complex and interlinked that a disruption in one part can trigger unrest in another, even thousands of miles away. Think of it like a spider web strung too tightly. Pull on one corner and you shift the entire net. That's what scientists now feared was happening, and worse, it wasn't being driven by natural plate movement, it was being driven by energy, solar energy. New models began to show something shocking. The magnetic compression from the recent solar flare, the one that smashed into Earth's field earlier that morning, hadn't just caused auroras and power grid flickers, it had energized the planet's crust. That energy, once diffused downward, began activating dormant stress points across multiple tectonic plates. Not all were strong enough to cause immediate damage, but the timing suggested that many had been right on the edge, primed and waiting for the slightest nudge, and that nudge had come from above. Geophysicists at MIT overlaid the sequence of global tremors with a satellite map of the Earth's magnetosphere during the storm's peak. What they saw made the room go silent. The tremors lined up with the areas of highest geomagnetic flux, almost perfectly. In other words, the places where the magnetic field had been most violently distorted by the solar storm were the exact same places now experiencing earthquakes. And it didn't stop. Each minor quake seemed to destabilize its neighbor. Like tension being passed along an invisible thread, the tremors began to build momentum. And this wasn't just theory. Airports in Manila and Osaka were grounded. Tsunami watches were issued for the southern Pacific. Volcanic sensors on Mount Etna began blinking for the first time in months. Because something was moving under all of it. That movement wasn't random, it was connected. The most haunting part? The timings were symmetrical. Not chaotic, not jagged, but smooth. Every wave, every tremor, every pulse, travelling outward from an epicenter no one could see, because it wasn't on Earth, it was in the sky. Cascade zones, it turned out, were no longer just geological, they were cosmic. And as the cascade effect continued to spread, reaching even the mid-Atlantic ridge and dormant Himalayan zones, one final question surfaced, one that rattled the minds of every scientist watching the data flood in. If the solar storm could trigger this, what happens when the next one is even stronger? Just after midnight UTC, something happened that instantly crossed the threshold from strange to terrifying. A magnitude 7.2 earthquake struck the Arctic shelf. Let that settle for a second. Not Alaska, not Greenland. But deep beneath the frozen seafloor between Svalbard and the North Pole, an area not known for tectonic shifts. Not in our lifetimes, not in recorded seismology. The quake didn't originate near a plate boundary or a traditional fault line. In fact, the closest geological data showed the Arctic craton had been dormant for over 400 million years, and yet, that night, the ice cracked. Satellites captured it first, a bloom of pressure waves rippling under the pack ice, lifting and splitting sections of frozen ocean. Then came the tremors, and then something no one expected: heat. Sensors on the European Cryosat-2 and NASA's IceSat-2 detected sudden thermal spikes, not from above, but from below. The seismic pressure had somehow released latent geothermal energy, pushing it upward into an environment that had been locked in deep freeze for millennia. Within hours, the ice shelf around the quake zone had begun shifting, not melting at the surface like in typical climate events, but breaking from underneath, as if the Earth was exhaling. The scientific community scrambled. Why here? Why now? What kind of tectonic event even could generate this type of rupture? Theories emerged. Some believed the geomagnetic shockwave from the solar storm had amplified existing faults far deeper than usual, what they called submantle resonance. That instead of triggering surface quakes, the energy had pulsed through the mantle's understructure, loosening deep pressure zones that hadn't moved in eons. Others proposed a magnetic alignment theory, that as the Earth's outer field twisted under the storm, parts of the core responded like a gyroscope under duress. It was only a model, but it matched the time signatures. And if true, it meant this quake wasn't just rare. It was impossible under normal conditions. The quake's location made everything worse. The Arctic seabed holds vast pockets of methane hydrates, frozen gas trapped beneath layers of sediment and ice. When destabilized, these hydrates release methane into the ocean and atmosphere. And following the quake, researchers from Norway's Fram Centre detected exactly that. Sudden methane plumes surfacing through cracks, hissing through the sea ice. Not enough to trigger global panic, yet, but enough to prove the system was shifting. Journalists tried to cover it as a freak quake, a one-off. But behind the scenes, emergency geophysical task forces were being assembled. Not for rescue, but for understanding. Because this earthquake defied every rule, the plates didn't collide. There was no major foreshock, no volcanic lead-up, no warning signs in weeks of seismic telemetry, just a single pulse, a downward flex in Earth's lithosphere, a crack in the deep shelf, and a magnetic event that reached beneath the crust to a part of the planet we barely understand. In Tokyo, a volcanologist whispered to a colleague, "If it can shake the Arctic, then nowhere is truly stable anymore." And still, the energy hadn't stopped. Seismic waveforms from this Arctic event began overlapping with signals from the South Sandwich Islands in the southern hemisphere. Some thought it was coincidence. Others were convinced it was feedback, a new kind of planet-wide harmonic. As if Earth itself was beginning to hum. The deeper scientists listened, the stranger it got. Following the Arctic shelf earthquake, a subtle but persistent low-frequency vibration was detected across dozens of seismic arrays, stretching from Greenland to New Zealand. Not a tremor, not an aftershock, something else, something continuous, global. It wasn't noise from machinery, not ocean waves, not glacial movement. The signature was too clean, too uniform. It pulsed with regularity, once every 8 seconds, then again and again. Like the slow beat of a planetary drum, At first, many dismissed it as a quirk in the sensors, a miscalibration. But then Japan's Earthquake Research Institute ran the signal through a comparative database of seismic anomalies going back over 60 years. The results were chilling. This frequency had never appeared before, not in any continent, not at any depth, until now. Some began calling it the Earth hum. Geologists, magnetospheric physicists, and acoustic researchers started working together, an unusual collaboration sparked by an unusual event. One of the more daring proposals came from a Chilean research group, that the frequency wasn't coming from within the Earth at all, but from the interface between Earth's magnetosphere and its crust, something entirely new. They called it magnetoacoustic coupling, a phenomenon where magnetic pressure from the Sun, especially in a superstorm scenario, could resonate inside the Earth's crust and upper mantle like a tuning fork. If true, it meant that the planet had been struck by the solar storm, and now it was ringing. Satellite telemetry supported this idea, while ground-level sensors detected the hum in seismic channels. Orbiting observatories like the GOES-17 and the Magnetospheric Multiscale Mission noticed.